it's time for some acid-base chemistry. We have not done hardly any of this at all. So, as you know, if you're here, it is possible that you are interested in learning some chemistry. And I do have a PhD in chemistry. I have been a professor at a university for many years. And so I love teaching this stuff. And I love ASMR. So I am here for you. Okay? And I love teaching requests. So always feel free to let me know what you want to learn about. Alright, so let's get going. And I wanted to start out with, if we're talking about acid-base chemistry, one of the things that I love using as an example of the power of acid-base chemistry is to talk about buffers. And buffers, first we want to think about what is the role? What's the role of a buffer? And so this is where we are talking about maintaining the pH, right? And that could be for any system, okay? But a very powerful system to talk about because it's something that relates to all of us. That is blood. Okay, so we'll be talking about blood. Okay. A very important one, okay, to maintain life. Alright. So, what is in a buffer? Okay. So all buffers contain very specific things. Okay. And it's always a weak acid. And it's conjugate base. Alright, now, you might not remember what a conjugate base is. So we could do just a quick review. Conjugate acid-base chemistry. That is a Bronsted-Lowry theory that is essentially talking about hydrogen transfer, okay? And so if we have a weak acid that is, let's just use as an example, carbonic acid, that's a weak acid, its conjugate base means that we have removed a hydrogen. So the conjugate base of carbonic acid would be bicarbonate. Okay, so here's just one example. And oftentimes this combination, it is in a very specific ratio, and it depends on the pH that you're interested in. Okay, so since we're talking about blood, let's show those buffer systems that exist within blood. And it's not totally coincidence that I picked these, because these do exist in blood. Carbonic acid and bicarbonate are in our blood. Okay, so you know what else is in our blood? Is H2PO4. But this is an ion, okay? And its conjugate base, once again, we remove hydrogen. So, H2PO4. And because we're always removing a hydrogen ion, H+, that's why we end up, here we start with a neutral, and we end up with negative, because we've removed H+. So here, H2PO4 minus is now 2 minus. So this dihydrogen phosphate and monohydrogen phosphate. Here's another acid-base conjugate pair that exists in blood. And then the other primary combinations that exist in blood, they have more to do with all of the amino acids. Okay, so the amino acids are mostly in proteins. They're not all in proteins, but many of them are. So we could think of them as, if we lump them all together, all these amino acids, we could just call them protein with hydrogen on it, generally speaking. Okay, and it's really, we're talking about an amino acid within a protein. And then when, again, H+ is removed, then that protein would take on an extra negative charge to it. Okay. So this is just really generally speaking. Okay, it's not specific entities like we're showing here. So within blood, a combination of all three of these buffer systems allows us to maintain the pH of our blood naturally right around 7.4. Okay, so all these together. I can move this up a little bit. Okay, and that is so important for our health and our well-being. When our pH varies outside of this range, our pH, okay, like I said, it's about 7.4. Okay, this is approximately is what I mean there. And what I mean by that is it's between the range of 7.35 to 7.45. Okay. So if it goes below 7.35, you have something called acidosis. Okay, your blood is too acidic, and you can get very ill from that. You could even die if it gets way below. And same with going above 7.45, you get alkalinosis. Again, very detrimental to your physiology. So we need to stay in here. So thank goodness we have all these different systems working together for us to maintain our pH. Okay. Let's do an example of looking at the bone. acetate buffer. Okay. And this is just a convention that very often the name of the conjugate base ion is used, acetate buffer, is used as the name of the buffer. Okay. So this is, as we just learned, as a weak acid has conjugate base. So what this means is that it has acetic acid, okay? And the formula of acetic acid, this is an organic acid, okay? It is a carboxylic acid, so it's often written this way. Sometimes you see it as O2, okay? But this is our acetic acid, and it's got that conjugate base, the acetate. Okay. Now, these are going to exist in roughly equal proportions, but we don't know the exact proportions until we've decided what we want the pH to be, or given a certain proportion, then we can calculate what the pH is. Okay. So what we're going to then do is I want to show you the equilibrium that's going on between these two, okay? And so in aqueous solution, we've got acetic acid, alright, and this will naturally equilibrate by deprotonating. We'll lose some percentage naturally of those hydrogen ions. Okay. It's a product here. Okay. And so this will occur to some degree. Now, how much does acetic acid break apart? If it was a strong acid, like if we were looking at hydrochloric acid, it would break apart how much? It would break apart in water nearly 100% because it's a strong acid. The hydrogen ion and chloride ion, those separately are more stable in water than the HCl molecule is in water. But in contrast, here we have a weak acid. Weak acids predominantly stay as a molecule. So there are far more acetic acid molecules in solution than there are the ions of it, the acetate ion and the hydrogen ion. So there are fewer. And we can't just say 100% or any specific percentage unless we have more information. And because this is an equilibrium, we can talk about exactly that. Okay. We can talk about the equilibrium equilibrium constant, and that will tell us some information about how much the acetic acid molecule breaks apart. So equilibrium constant, symbol for that is capital K, and the sub A is convention used for acids breaking apart in this way. We start with the molecule and show it how it is deprotonated. And equilibrium constants are written as products over reactants. So we could write this in terms of the equilibrium constant expression. Here's our products. Hydrogen ion. And here's our whole molecule. Okay. Alright. So this is the expression. Okay, but we want to know what the actual value is. And this is something that you can find on tables. So for acetic acid, it happens to be 1.8. To the minus 4. Okay. And by the way, right here is our indicator that this is a weak acid. Okay? If the Ka were 1, then we're looking at something that's closer to half of them broke apart. But one of the ways that we generally define a weak acid, if it's closer to 95% or 90%, 99%, around there stays the molecule, and only a small percentage hydrogen ions are released. Okay. So, from this, I wanted to point out that in a buffer, we've got weak acid, conjugate base, and by adding in that conjugate base with the acid, this is an example of LeChatelier's principle, where that conjugate base is going to be added in and it shifts the equilibrium back towards the acid. So it's a very ingenious setup here where you've got a base that can react with the acid that's there. If there's extra acid, shift it backwards. But also, if you were to introduce, say, a strong base like hydroxide, then you have plenty of acid there to react with a base to then send the equilibrium back this way. But you're still going to have some of both of these ions that are ready. They're ready and poised to be able to react with either an acid or a base that you might add to either side. So that's generally the concept of how a buffer works. As long as you have both of these present, then, and especially if you have some extra conjugate base in there, then you're ready to deal with whatever is thrown your way in terms of acid or base to maintain that pH. Okay. Now, let's move on to a little bit more of the quantitation of buffers. Okay, so I'm gonna, let's see, make some more room here. Okay. called the, oh come on, I love this pen, and then sometimes it's frustrating too. This is called the, oh maybe I need more ink. Okay, so this is called the Henderson-Hasselbalch. Equation. This is so helpful for working with buffers. Okay. And so the way this works and why it's so helpful for determining pH is that as long as you know what we call the pKa for the weak acid, okay? And notice how up here I gave what the Ka was, and pKa can be easily determined. Make some more room here. So the pKa can be calculated very similar to pH. Okay, if you remember how to calculate pH, it's minus log of the concentration of hydrogen. And pKa, you can think of P as kind of like a function. In this case, the function is taking the minus log of something. Okay, so if we take the minus log of the value of the Ka, that gives us the pKa. So we could do that for acetic acid. Let's just do that really quick. We could take the minus log of 1.8 times 10 to the minus 10. And if we do that, we get 4.74. Okay, so here's our pKa of acetic acid. So that would be able to go there. Okay, but this Henderson-Hasselbalch, this is it's used to determine the pH of a buffer. So that means we need to take into account the fact that we put some of the conjugate base in there, and that changes this equilibrium, right? So if you put in your conjugate base, LeChatelier's principle says we're going to go backwards, right? So that means we will have less of the products, more of the reactants, okay? Have a little bit different ratio there. So that means that, and this equation can be derived pretty easily, by the way. I'm just not going to do it here because we want to get this more quickly to the point here. Okay, so this is going to be a ratio of the conjugate base. Okay, that's up in here in the numerator. And then this is a ratio with the denominator, the concentration of the acid. essentially we could think of it as that it's over here. Or I should actually, this has been rearranged. It's actually over here with the pH. We took pKa of all that's left over, and we end up with this ratio here, pH over here, pKa. So this overall equation is going to help a lot with buffers. And we can ask a lot of different kinds of questions. You could put in concentrations of these and measure the pH, and then you could calculate pKa. Or maybe you know the pKa of a known acid, and you have a target pH that you want, and then you could calculate the appropriate ratio of how to mix these together. Or the final combination, you could know the pKa, and you could mix together a certain ratio of these, and then you could calculate the expected pH from that. Okay, so lots of very useful examples of how you can use the Henderson-Hasselbalch equation. Okay, so let's take a look. Let's do an example. I always like doing examples. So, let's see. So, let's look at this. What is the pH? We'll start here. Oh gosh. Oh. Sorry. And I want to start with a solution that is okay. So I'm going to start with a solution that has only acetic acid, okay? And so we can look at that as kind of like the baseline, okay, the starting point before we add the acetate, before we make it into a buffer. And then we have a set point for comparison. Okay, so what's the pH of a solution? That is, let's say, oh my goodness, that's 0.6 molar. Okay, 0.6 molar. Alright, acetic acid. Okay, just as a reminder that this is just the acid. No, not a buffer yet. Okay. Alright, so for this, we can use just knowing the Ka. We do need to know the Ka, okay? So if we look up here, we have all the information that we need. Okay, we know that it's 0.6 molar. And we know that this is a weak acid. So we can approximate that 0.6 here will stay within one significant figure. We won't lose much of this. Small amount will be broken apart, and that these are equal stoichiometrically, 1 to 1 to 1. These are all equal to each other. Okay, So that means that we can write this Ka equation as based on what we see here. These two are equal to each other. So we could say that we've got our CH3COO times H plus. And this will be over the concentration of acid, which I meant to actually put this in parentheses. Here's our concentration that's known. Okay, our 0.6, well, 0.6 molar down here. Okay, but remember these two are equal to each other, and this is known. So we have 1.8 times 10 to the minus 5 equal to each other. So let's just call them X. X equals H plus, and H plus equals acetate concentration, because remember it's 1 to 1 up here. So we can say X squared, since they're multiplied together, divided by 0.6 molar. And if we then solve for X and know that it's equal to H plus, okay, we end up with it being 3.3 times 10 to the minus 3 molar. And then we can calculate the pH. Let's just do that here. Minus log of H plus. That's this. Goes there. And we end up with the pH being 2.48. Okay. So this is the pH of our acetic acid solution. Okay, of our 0.6 molar acetic acid solution. So now we are going to adjust the question a little. And we're going to ask, what is the pH of a buffer that is, so now we're going to keep this the same, 0.6 molar acetic acid. And mixed together in there is 0.8 molar acetate. Okay. Now the origin of the acetate is probably like sodium acetate or something like that, a salt that's been dissolved in there. You can also titrate in to acetic acid to cause acetate to be formed. There's various ways of doing that, but the net result is the buffer has these two concentrations of weak acid and conjugate base. Okay, so now we get to use, since it's a buffer, we get to use the Henderson-Hasselbalch equation. Okay, our equation. Got pH equals, alright, our pKa. Do we know the pKa of acetic acid? Why, yes, we do. We calculated it earlier. Okay, this is a very specific value for acetic acid. Every weak acid will have its own Ka. This shows how much a specific acid breaks apart. And that has to do with the bond strengths, all sorts of characteristics of that specific molecule. So these are specific values. And also they've been measured on tables. They're on standard conditions, 25 degrees. Okay. So our pH, we can now put in our pKa value, 4.74 for acetic acid. And then here's our adjustment. Whether the final pH will be greater than 4.74 or less than will depend on this ratio. Okay, so let's see what it's going to be in this case. We've got our conjugate base is 0.8, right? Molar. The concentration of the acid is 0.6 molar. Okay, so if we look at this ratio, we see 0.8 over 0.6. This is going to be greater than 1, and the base 10 log of a value that's greater than 1 will be a positive. Overall, this will be a positive value. So we will be adding a positive value. So the pH will be higher than it would be if that acetate were not there. Okay, so we expect the pH will go up. Alright, so that's our intuitive sense. So let's go ahead and calculate. And I'm just gonna separate out these calculations. And it turns out this value is positive 0.12. And so, indeed, we end up with a pH that is 4.86 for this particular buffer. Okay. I did want to mention that if this ratio were, let's say, the opposite, if it were 0.6 over 0.8, then this ratio would be less than 1. And the base 10 log of a value that's less than 1 is negative. And so you would end up subtracting something and get a value that's less than 4.74. So just something to keep in mind there. Okay. But here is our pH of this buffer that we made here. Okay. So I hope that this was helpful for you. There's a lot more that I'll be doing with acid-base chemistry, believe me. But I wanted to talk about buffers because I've gotten some questions about buffers, so wanted to go over all this. And I really hope it was helpful. Thank you so much. And thank you, really, truly thank you for all of the really positive feedback and really nice messages. It's kind of funny because today I got my first a little bit negative comment on my channel, which I think is really good. this is boring. And actually, I took it a little bit as a compliment, because if people find it boring, then maybe that will help them sleep better. And I am all for that. I'm actually, if you're listening to this right now, I'm very impressed that you made it all the way to the end. So, congratulations. I should give you a prize for that. But anyway, thank you